I'm going to do some practice exercises using the specialized micrometers that we covered in the last video. So go ahead and visit the Pragmatic Metrology website so where you can download this exercise, get the prints that you need, find 3D CAD models if you want to make this part or 3D print it, and you'll need the step shaft, the angle block, and take a look at the parts that you have. These two parts are not the best for working with all of these gauges, but we're going to practice using them. But take a look at other parts you have that might work for um, these gauges, especially things with internal or external grooves, which these parts don't really have those features. I guess we could add an internal groove to these features or external grooves if we wanted to as well. So let's look at our exercise description, which says practice using the specialized mics and compare to standard OD mics and calipers. So we've learned about standard OD mics, we've learned about calipers by this point, and we're just comparing how these help you, how maybe these are maybe more complicated than using a caliper in some situations. So think about that as you're using these gauges. Go through the calibration checks for each gauge before you use it, and look at the prints for new opportunities to use new styles. So we should be looking at our prints to figure out when we can do direct measurements with the new gauges, or when an indirect measurement maybe end up being better for us than a direct one. So let's just get started and look at our instructions. So for each gauge, check your micrometers for good calibration, inspect for cleanliness, practice calibrating and setting zero, and check with multiple blocks, multiple sizes. Look for bent frames. Are your anvils damaged? Hold up your anvils to the light when you do it. Number two, see the following page for specific measurements for each gauge. So that looks like kind of a grid pattern. We have the gauge here on the left, and then our different parts, our step shaft, our angle block, and parts that you have. So we're going to follow that grid to practice our measurements. And again, explore your own parts and explore the drawings for opportunities for you to practice. For tool practice, practice adjusting your pressure and holding the mic in different positions. And use the gauge blocks as a standard. So when you're not sure about a mic, practice on a known diameter, a known distance before you measure your parts, so you can get your feel down and your practice down. So we're going to go through pretty much one by one. As I mentioned in the last video, I don't have a blade or a pin mic with me. I do have the disc mic, and it's pretty much the same situation for all three gauges. So if you want to practice with those, please do. Please follow these instructions, but I'm going to demonstrate the disc mic on the step shaft, the angle block, and then I actually have this other part here which I'm not providing. It's kind of just a one-off part that I happen to have and has a few good features for us. So look for parts like that. So let's clear off everything but the disc mic and the OD mic. I'll leave that close by. So we're going to start off with the step shaft, and it says, measure the 508 diameter. We could easily do this with an OD mic, but let's see how it works with a disc mic. So open it up. Again, it has a non-rotating spindle. There's a little bit more resistance when I open this up. And we just hold it like a typical OD mic and grab on. We're getting a lot more surface area because of how big it is, so I have to be careful about it. It's definitely rocking. It's hard to show up on camera, but it's definitely rocking a little bit. So there might be a taper. So I'm looking at 517 and a half, and I'll rotate 90 degrees and check again. 517. Let's check at the base. 514 and a half. There's a little bit of rock, so there's some taper. 514 and about 3/4 or so. So there's some taper, and I could feel that and how it was rocking. And in the middle, I'm about 515, which matches the pattern. I really hope you guys can see what I'm reading. It's a little bit hard to see up on the screen here, but check the secondary camera feed, and I'm reading out my measurements just like an OD mic. So there's a little bit of taper, and in fact from 508 to plus or minus 5 from the title block, that's out of print. So since I'm using a new micrometer, I'm going to do a sanity check with my caliper. Yep, about 518, close to what I got with the mic. 511. So there's definitely a taper, and I measured it accurately with the disc mic. So you could keep going on other diameters with this part if you want, and compare to using your OD mic, and you'll get a different feel. With the smaller anvils, it's going to feel different. It's not going to rock quite as much. Actually, it's going to have should have a little better feel, because you're getting a tighter anvil, so more surface area is being contacted in a percentage fashion. Percentage-wise, it gets more contact than with the larger diameter. Actually, and I kind of jumped into this. I checked zero in the other video, but let me show you about checking zero and checking calibration. So we will close this down on a piece of paper to clean it out. And a little bit too much pressure. Drag the paper through. That should help clean it out. And go to zero. And I've pretty much got zero. So I think in the other video I had a tiny bit off, but maybe I just didn't clean it well enough. Now it's looking pretty good, right at 0. And I'll check halfway through stroke, just to reinforce that you need to kind of check your strokes. So I'm going to grab 0.5 and verify that. Again, I pretty much got right on 0.5. Maybe a 1/10 different at most, but fortunately I don't have a 1/10 scale anywhere on here. So last thing to do, I should have done it while it was closed. I can't really demonstrate on the camera, but hold it up to the light and look for any gaps. Don't look directly at lights, obviously, but I don't see anything. If I put it up to a white background, it looks perfectly closed to my eyes. So it's in pretty good condition. Now let's do the angle block. So the angle block says to measure these steps, 0.315, 0.610, 0.840, and the overall thickness. So that's a direct reading. The way this print is set up, those are direct thicknesses. So we can just grab our gauge and let's see, I'm at about 310 and 2 or 3/10, 310 and 3/10, let's say. And I'll move over to the other end of the part, about 310 and 2/10 again. So you want to check multiple places if you can, right? Because your part might have taper or some error twist, might not be flat or parallel. So overall, what am I supposed to be? I'm supposed to be 610, and I'm at 606 at that point. Let me check the other side. You can kind of see. I'm at 606, maybe a 1/10 smaller. So it's pretty parallel, and I do feel like I'm getting great contact. I'm getting a lot more surface area on the back and on the front as well. And it's a bigger anvil, so it actually feels really secure compared to the standard OD mic. Next up should be 840. And let's see if, yep, I still have enough reach. So I'm rocking it with my arms in both directions, this way and this way, so that it seats properly. And I'm staying away from this inside radius that the corner most likely has an inside radius, so I'm backing off of that a little bit. And using my touch, I get 825 plus 11, so 836. It's supposed to be 840, so in print. Let's check over here. And 836 and a couple of tenths. So in print at all locations. Let's double check with our caliper. 310, 311, 606, that sounds about right. We're 610 on the print. 837, I think I was getting 836. So overall, looking pretty good. And just remember the way the caliper works and the way the disc mic works, or any other mic, is they have different anvil registrations, different accuracies. They're going to give different numbers. Just the nature of it. But I'm going to trust the OD mic a little bit more because I know it's more accurate than my caliper. But my caliper is grabbing in a different way. It has much larger jaws. So that's always the trade-off between gauges. They often operate differently and don't give you the same number. But as a quick sanity check, it's a great way to know that I was using this gauge correctly. Oh, I think we're supposed to do the overall thickness, which was 1 inch. So this is actually a pretty good tool for that as well, because I've got big anvils. I'm a little bit less than 1 inch. I'm at 0.998. I'm almost to 0.998 and like a tenth under that. And then I'll check a few other places. I'll check back on this side. Oh, I'm over 1 inch. I'm 1 inch and about 2 tenths, 3 tenths. Over here, 1 inch, 1,000th and a half. So 1.0015 on this end. And we'll check over here. There's definitely some taper issue, about just under 1 inch, about 0.9998 or so. From what I'm seeing. So overall there's a little taper, and I'll grab my caliper sanity check. This should be larger on this side. 1.003. There we go. 1.003. Come on. I don't know why the shadows are so messed up in this video. And yeah, 0.997 on this end. So there's a little bit of taper. If the shadows are really not helping you see up here, please check out the secondary camera feed where you can see it a little bit clearer and follow along easier. So last thing we had to measure was 0.4 step depth right here. So we're not going to be able to do that directly. We're going to have to use our overall thickness and subtract our flange thickness. So let's measure our overall thickness while the mic is still open. And let's say 1 inch, 0.001 and a half. And we're going to subtract whatever we measure for our flange thickness. And that is about 0.601 3/10. So 0.4 and 2/10. And it's pretty much exactly what we were looking for. So we're pretty good there. So that's it for the standard exercises. If you've got, an OD groove part, you can go ahead and measure some of your thickness of your grooves with this as well. That will help. So you just got to make sure that there's no interference with the tapered body of the anvil. But otherwise, kind of twist it and rock your part and clamp down. And it doesn't want to seat there very well. Let's try another spot. There we go. Feeling a little better. And 0.2 and 0.4. 0.20045. Let's see if I can even get pretty close to what I get with a caliper. So I just noticed I could do it. So I could, if our print were for some reason set up to go across this distance, you could do that too. So, you got some interesting capabilities, and just gotta twist it, rock it in. And I'm reading 0.642, if I'm doing my math right. 0.642. And let's check with our caliper. Yeah, about 0.644, 643. So that's a great tool for using for outside flanges. We're going to move on to the next tool. Since we don't have a blade or a pin, let's move on to the depth mic. So for the step shaft, we're going to measure from both ends the depth or the height. And with the PM feature, we'll do our step 0.315 with a shot math, our step 400 with a shot math, our depth 350, which I believe is the slot, and the depth, the round slot, 0.3. So, in order to measure this, I'm going to have to involve a V-block to help me hold my part. So, if you haven't seen the surface plate videos, I explained how you can use V-blocks to set up fixtures and just stabilize your setups. It's a little bit out of... Alright, I think it's stable enough as it is. So first of all, let's look at our print. I have it set up to measure from this distance down. So the nominal should be 5 minus 4.008, so it'd be 0.992. Okay, so that helps me pick which anvil I need. I need the 0 to 1 anvil, and I have the 1 to 2 anvil loaded up. So I'm gonna switch out my anvil and check my 0. On the surface plate. Okay. Go by feel. And what do you know? I'm a little bit... See, it's a little bit of a bad 0. So I'm going to disassemble, try to reassemble. And I got a much better 0. Although it's not perfect, just by disassembling and reassembling, I got about 1/10 of error. Small, which I'm going to live with. I'm not going to chase it. As I mentioned in the training video, there's usually a way to get a wrench on here. I'm just not familiar with this style of gauge. I looked it over closely and I couldn't figure out how to get the wrench on to rotate the sleeve, but that's normally how it's done. Let's also double check our full stroke at 1 inch, because we are going to be working with pretty much the full stroke for this measurement. So I've got a 1 inch Joe block. And I've got a little bit of error. Ooh. Check that again. I've got about the same amount of error I had before. So it's fairly linear. I'd say maybe another 1/10 of error came up. I really apologize for these shadows. I'm not sure what's going on, so check out this camera feed. So, if we're going to work from the top, you know what, I am going to need this little stabilization. So we're just going to drop this down, and we're going to try to avoid the radius that's left over in the turning process. And I've run out of stroke. So this is already, that's supposed to be 0.992, and I've run out of stroke on my gauge. So let's double check with a quick depth check with a caliper. 1.169. It is way out of spec. So let's change over. Actually, let's do this one later. Since I just zeroed this anvil, I don't want to mess with it again. So we're going to check the other side while I still have this anvil in, the 1 inch. So we'll come back to that end and clamp down so we can hold it. Alright, and this is supposed to be a direct 1 inch. Coming off of this end, it's supposed to be a direct 1 inch measurement. So let's try again. And I actually have good contact now. So it can be very easy to jack up the gauge with a, as you come down, it can be very easy to just keep going and jack up out of position. So we want to watch for that. But if we take a look at our reading, I'm just at, actually I think I bumped it. Let me do that again. And I'm just at about 6 thousandths past 1 inch. So 1 inch and 6 thousandths. And let me double check with my caliper, just because this is a little bit of a tricky measurement. What do you know? 1 inch and 6 thousandths. So a little bit out of spec. 1 inch plus or minus 5 thousandths. I'm 1 thousandth out of spec. And normally I would go around multiple places, just like any other gauge. Check multiple places. Have a light touch. Okay, it stops there. Actually a little bit worse. Now I'm at 6.5 thousandths past 1 inch. If you can see that. So it's a little bit out of spec. So these are positive external features, and we're going to shift gears a little bit and move over to the angle block. And we're supposed to measure this thickness using the depth gauge. Now we're not going to be able to measure it from here to here. We're going to have to come off of the top side down and use the overall thickness. So I'm going to grab my caliper to get the overall thickness, which is fine for practice. 0.997, I'll put that in my calculator. And then we're going to measure from the top surface down to the step. All right. And I should be able to hold everything so you can see it. Give you a nice clean background. So I got pressure here, holding it in place. And my anvil, let's see if I can. Is this helping at all? It's not. I don't get it. I haven't changed any of the lighting. I haven't changed anything. But, well, there's my gap. I need to be a little bit away from the side wall. So I'm pushing it away from this side wall so it's not rubbing, and then I just bring it in until it touches. And then a little bit of light touch, and what's my reading? My reading is 0.686. So remember the depth micrometer numbers are reading opposite of an outside diameter micrometer. So remember that. And just take my word for it or look at this camera. I've got 0.686. So we'll do that subtraction. And 0.311. So that would be our shop math calculated 0.315. So let's take a look at what the caliper told us. I don't remember at this point. Yeah, pretty close, 0.310. So got a good sanity check there. Next up, I'll measure the slot, the square slot depth, which was 0.350. So track this a little bit. And now I can get both sides of the anvil on there and just drop it straight down. There we go. And my reading is, let's see, not quite to 350, I'm about 340. Oh, 348 and a half. Yeah, even I'm having trouble reading this backwards gauge. So 0.348 and a half. You know what? We don't even need the surface plate, so I can leave the papers down. And I'll check the other side of the groove. And again, about 0.349. So overall, we're in print. Next up, I'll do the depth of the round slot, which is 0.3 depth. So again, we'll open this up. Now this is a time where I'm going to hold it put some pressure with my two fingers and bring it down. Oh my goodness, this is just ridiculous. Well, looks great in this video. Maybe you should just watch this whole video from this angle. Alright, so it's bottomed out. We'll pull out our gauge and take our reading. So it's actually not 0.3, it's closer to 0.293. So according to this, it's still in spec because we have a larger tolerance with our 2 decimal place accuracy. So with 2 decimal places, we have plus or minus 10. So we're within spec on that one as well. Let me just verify with the caliper, since we're practicing a new gauge. .295, 294 I got on my first measurement. So I'm within the ballpark of the depth mic. So, I mean, that's pretty much it for the depth mic. You can use shot math, you can do direct, different features and different methods. Okay, we're about 30 minutes into this video and we've just got, we don't have a groove mic to work with, unfortunately, but you can grab some parts with some internal grooves and some external grooves and check those. The multi-anvil. So we're not really, nothing on the step shaft to check with a multi-anvil micrometer, but we're going to measure a couple of parts. We're going to measure the angle block to find the hole location, and we're going to do measure the runout using this part here. So maybe this, I hope this is helping. All right. So first we'll do the hole location. So we have a 970 through hole, and we have a 1.490 in the X direction, and we have a 1.005 in the Y direction. So before I get started, I need to know the size of the hole. So I'm going to grab that with the caliper, 0.969 and 0.969 pretty much everywhere I check. So we'll say it's 0.969, and our radius is going to be 0.4845. I don't think I'm going to remember that, but we'll keep it in the calculator. So since I don't have a multi-anvil micrometer, I can still use this tube micrometer the same way. First thing I'll do is close it. All right. And check for 0. It's got a nice ratchet to it, and get out of the way. Reading a pretty good 0. I'd say it's right on 0. So we're good here, and now let's do the 1.005 first. That'll be a little easier. So we're going to grab this edge and the bottom of the hole. And it's going to self-center. You can kind of rock it into place, twist it in both orientations. And I'm reading about 0.5, 20 and a half. So let's add that to our number. Plus 0.5, 20 and a half. 1.005 exactly. So we're reading pretty good on 1.005 exactly. And next up, we'll do the X direction, which was that longer distance. So we're going to have to open this quite a bit more. And it is kind of going to self-center as long as you kind of rock it and close it at the same time. And now I'm reading 1.004 and 2/10. So we'll do 0.4845 is the radius, 1.0042 is the distance I just got, and 1.488 7/10. Compare that to 1.490 and we're looking pretty good. So if you didn't want to use this gauge here, some other methods you could use is a caliper. You could get those same distances with a caliper. And your other options might be a surface plate and a height gauge. You could set it up on a rock and watch those videos, and I show you how to measure a hole location using a surface plate and a height gauge. But the other application besides finding hole centers is going to be runout checks, symmetry checks. So as I demonstrated in the other video, I'll do that one more time. We'll check the runout of the outside and the inside diameter. And we're just going to grab the inside and the outside in multiple locations and look for TIR, well not TIR, but look for the differences. So about 249 2/10. Let me write these down. .249 2/10. 0.252 and 0.248 2/10. And let's see, that's about the same as before. I'm going to try to get all four. 0.251. So I'm looking for the low and the high. Oh, there's the low, 0.247. So my overall distance from low to high, my low is 0.247 and my high is 0.252. So my runout difference that I got is 0.005. And you know, that's a great way to check it with a tube micrometer or a multi-anvil micrometer. We could double check ourselves with a caliper. There's a high of 253, 254, 251, 248. So we are 248. So we are in the ballpark with the caliper as a sanity check. And that's just telling me the thickness is different, so therefore the runout is different. And maybe the thickness is different due to a diameter difference. 1.254, 1.254 looks pretty consistent. Let's check the inside. 0.754, 0.754, 0.754. So it just looks like a positional error when the counterbore was put in relative to the outside diameter. And that's a runout error. So as I mentioned before, setting this up on a surface plate might be a better application for runout in general, but to do that is going to be very difficult with this very shallow diameter, and I can't use those rough outside diameter as a datum, so it may be easier to do it with a hand tool. Well, I think that's it for all of our practice exercises that I can do for you here. But please, look for more applications in what you have and how you can practice and what parts you are using, what parts you're making. But let's go over a few discussion questions and then wrap up this video. So number one, how easy and accurate was it for you to adjust the micrometer calibration? What issues did you have? So, it's pretty much a standard OD mic calibration in many of these cases. With the depth mic, you saw me kind of struggle with, I didn't find the way to calibrate this one, so I had to, try to reassemble it, clean it, and make sure it gets good anvil contact. But for the most part, it's pretty straightforward, like standard OD mics, but some of these special ones may be more difficult. What effect did pressure have on your measurement? Do you prefer touch, ratchet, or friction thimble? And it made a big difference for me. I pretty much always went with touch because of all the unusual contact. I like to get that feel myself rather than rely on the ratchet. But that's up to you. That's something you should practice. With the tube micrometer here, I actually do feel a little bit more confident using the ratchet because I can get really good self-centering anvil contact. Number three, what features and tolerances were made easier with the new styles? Well, I think you saw in a few cases, I could measure this whole location with the multi-anvil tube micrometer very quickly. Same thing with the runout of this little diameter piece here. The depth micrometer kind of makes doing these steps very easy and accurate compared to using the caliper. Although the caliper is usually quicker and faster, it's not quite as accurate. The disc mic helped me get some more surface contact on these flanges, so I like that. There's and actually the disc mic actually allowed me to get some of these groove thicknesses that I couldn't even do with anything else I have. So they will help you. Keep looking for more opportunities. Number four, on your lab worksheets, identify the gauge that is best suited for inspecting each feature from all the gauges we covered. So you could do that with the prints. Just kind of circle or highlight and say, yeah, I would use a disc mic here. I would use a groove mic or a multi-anvil mic. But also think about what you've already learned. Just because these gauges can do those features, it doesn't invalidate using a caliper or a micrometer. But in some cases, it will be a better tool. In other cases, your standard tools are better. And we were just using them for practice. And then number five, which of the new gauges we covered are capable of gathering a better GD&T measurements than our standard OD mics and calipers? So identify the gauge, the GD&T, and the feature type. So if you haven't watched the GD&T video, maybe this is not a good question for you to answer right now, but to give you some context, the runout check with this diameter, that's a good tool. Maybe not always the best. Surface plate might be better, but in this case, it was a better tool than the surface plate. You can do true position, because true position or position error is just redefining the tolerance zone. You still need to find the center of the hole, and using the multi-anvil to find the edge of the hole and then offset by the radius, that is a pretty good, accurate way to get a true position tolerance or position error. Parallelism might be a little easier with larger anvils and bigger disc mics. So there are some applications where these will help with, specifically with GD&T, and other applications like, the depth mic I don't think is really going to help you with a lot of GD&T. Maybe a parallelism if your plane needs to be parallel as it goes down, but anvil is so small. There may be indicators, maybe a better check, a CMM, even a caliper might give you a quicker, faster verification that it's bad. But a depth gauge would still give you a very accurate way to do it if you wanted to. So I'm not going to tell you not to. Just make sure you think about it and choose the appropriate gauge based on the tolerance. Well, I think that's it. I want you guys to keep practicing these gauges with the parts that you have, and I want to thank you guys for watching. Please check out the website for more of these practice exercises and training videos, pragmaticmetrology.com. And I do want to thank, as I always do, the Laney Community College in Oakland, California, Machine Technology Department. Let me use these parts to demonstrate how these gauges work. They have a really good program there for manual machining, CNC machining, inspection and metrology, maintenance, CAD design, blueprint reading. They have a really great program to get you into the manufacturing industry and get you a lot of exposure to good practices and experience. So they have certificates you can earn, like inspection certificates and machining certificates. You can get an associate's degree if you do the 2 years of coursework, and you can do your apprenticeship courses there if you're an apprentice or you want to be an apprentice. You can do your classes there at Laney. So again, it's a great program, and if you're doing any of these classes, certificates, apprenticeships, whatever, you're really going to be helping yourself in your career to stand out, because manufacturers are looking for this kind of classroom experience. So that's the Laney Machine Technology Program in Oakland, California. So please take a look at their course offerings if you're in the Northern California Bay Area. And then please check out, again, my website for more of these videos on gauges and the concepts that will help you, when you're using these gauges, and more exercises. So thank you for watching, and I'll see you for the next one.